Welcome to the video on multiplying vectors by scalars. Now in this video I'm going to kind of make assumptions just to kind of let you know beforehand. So for example, when I'm referring to scalars, so those are going to be just numbers for us, so there's no direction at all that we're talking about. And I like to designate scalars just with a K. If there's multiple scalars, I'll put a subscript. So for example, it might be K1 or for instance K2, etc. And I will, assume that they're going to be elements of real numbers. So they're just basically numbers that we would have. Now for vectors, so the assumption within here, so for vectors, I love to write vectors just with a small v. Okay, sometimes I'll put, which I should put, but I'll drop it at times, although I'll try to keep it consistent for this video. You put the arrow on top of your v just to designate that this is a vector and it has actually a direction. And if you recall, so for any vector, what you have is you have a magnitude, which we designate with the absolute value, and then it also will have a direction. And that particular direction that it takes on can be given in various different forms. It can be given with respect to the true bearing. It can be given as kind of quadrant bearings, or an angle with respect to some horizontal or something else. I can put a video up above there for you if you want to recall all of those different ways of designating vectors with various directions. Now, this video is only about multiplication of scalars by vectors, and it's actually not that difficult, and it seems almost very intuitive that you would think, why would it be any different? Once you watch the video, you'll see, well, of course, if I multiply something, because you're so used to having numbers, it seems that it's kind of elementary. But it's not as elementary because of the fact that with vectors, you do have these directions. And we want to be able to see if what we do with numbers, as we scale proportionally, numbers up or down, if that's the same thing that happens to actually vectors. Now, it is true that it happens to vectors, especially when you're just kind of beginning, you're either in grade 12 or maybe your first year studying these components, which you will utilize maybe for physics or for other applications. Then you want to be able to see that the scaling by a vector, scaling by a scalar of a vector actually just kind of either moves it up or down, or possibly changes its direction by 180 degrees when you're multiplying by a negative. And that's exactly true. So here, in terms of visual representations, if you would take this, now I'm going to just take a vector and let's assume that it is kind of to the, I guess in this case, east, direction, or at 0 degrees to the horizontal. And that particular vector, of course, we can, make it bigger or smaller. So let's say that maybe it occupies for us in here. I'll make it occupy 3 squares. And I'm going to zoom in here. And now, if I'm going to call this vector v, so that would be my actual vector. It has a certain magnitude. We designate it with arrows, but really, those arrows are just kind of representations for us. So it means that that particular vector has a magnitude and it has a direction. And that direction can be anything. Now, in this case, I made it horizontal at 0 degrees, but of course it could be anything we like. Now, what if someone comes along and now says, okay, so well, what if you took this vector now and you're going to be multiplying it by some scalar? So you're going to take this, you're going to multiply it, and you're going to do this, and now, what is the result? At least what would we assume? Now, of course, it depends on this k. How big is this, right? Is it positive? Is it negative? So on. So for the moment, let's assume that it's just positive. And for instance, maybe k is equal to 2. So what would that mean? Well, intuitively, you would think that our actual vector, so the original vector that we would have, it would just simply be twice as big. And that's correct. So what happens is when you're multiplying by a scalar, so for example, if it's 2 or if it's any other number for that matter, you're going to make it bigger. Now, if it's going to be less than 1, so if you multiply it by 0.5 or a half, then it's going to be half its size. But the direction doesn't change when the scalar is positive. So the direction is identical. So if I took this, okay, a particular vector, I'm going to kind of duplicate it. I'll put it just above, but of course you can assume that it's right on top. So if I was multiplying it by 2, this would just simply be twice as big. So what would happen is if this is one of these vectors, I'm going to duplicate it again, okay, within here, well, twice as big, okay, it's like adding 2 of the same vectors together. It's just like multiplication of numbers, right? If you have 3 and you multiply it by 2, then you're going to get 6, or that simply just means you have 3, plus your 3. So this is what we would have. So we would have a resultant vector of twice as big as the original. So let me just kind of remove this and take this vector, okay, and then stretch it out, okay, so that now it is twice as big. But what is twice as big, right? The angle is not twice as big. The angle actually stays the same. Now, of course, you would say, well, if the angle is 0, if you make it twice as big, it would still be 0, right? Because 0 times 2. But of course, the angle is just relative to something. It's 0 to the horizontal, but it could be at 45 degrees or something else. But you don't actually touch the angle at all when you multiply by scalars or just by simply numbers. All it does, it actually impacts just the magnitude itself. So that's what happens. So this, okay, if I was writing it out, this would have been 2 times the original vector. That's what we would have. And again, magnitude is twice as big, but the direction is the same. Now, the only time that the direction will change is if you actually take the vector and you multiply it by a negative scalar. So let's say instead of multiplying by 2, maybe you multiply it by negative 2. So that's what happens. The negative, okay, actually gets absorbed into the vector and it makes it the opposite vector. And then the 2 would just simply means now that it's twice in magnitude. So what would happen is, okay, something like this. So if I wanted to go ahead and then multiply this, for instance, by negative 2, so this is what I would do times the original vector. Okay, this is the same thing as saying, well, you're multiplying by 2, and then this negative, okay, gets absorbed. And as you can see here, so if we write it like this is just the opposite vector. So it just goes in the opposite direction. And that's exactly what happens. So if I would do that, right? So let me just kind of take this particular vector. Let's duplicate it. And, maybe I will change the actual color here. So let's make it kind of blue. So what would happen is it's certainly twice as big, but now it's opposite. So it means it is now in the opposite direction. So it's going to be going in this direction. I'm going to bring it back in here. So that's what would happen. It is twice as big, but in the opposite direction. And that's all that scalars do. So scalars just scale. So they either will scale up, scale down, and possibly change direction if they are negative. So that's what you want to be able to think about. And now there's various properties of these multiplications by scalars that you have. You have run some of these properties when you were talking about, for instance, the addition and subtraction, okay, of vectors. So you had something like commutative property, associative property, okay, kind of the identity property. So if you forget that about additions and subtractions, I did it towards one of the end of one of the videos. I'll put up a link up above there and you can check that out. Now in here, those properties also extend to multiplication by scalars. Now what I mean by that is here they are. So here is something that we would know, okay, and have. Now we don't have necessarily a commutative property, okay, within here in terms of how you're going to be multiplying. It doesn't, honestly, the commutative could still be there. You can still take a vector, multiply it by a scalar, but that doesn't really make sense, okay? So, we take the scalar and then we scale the vector up or down or possibly change its directions. So the properties that we actually do run into with multiplications are these. The first one that you see here, which is called the distributive property, that shouldn't really be anything extraordinary for you, right? So if you take this property, so I'm going to just take this out, okay, I'm going to copy it for myself, and actually since I have a little bit of space up above, I'm going to put it in here. So the distribution, you might recall, if you were not talking about vectors, if you were just talking about variables, so if v1 and v2 were just some variables, so some quantities, okay, and you weren't even thinking about vectors, so in terms of directions, you would look at this and you would say, well, yeah, of course, I mean, probably, I don't know, in grade 10 or something like that, you know, you have learned the distributive property where you can distribute this across a bracket, right? And what you would get is, you would get exactly this right here. That shouldn't shock us, right? That was indeed the distributive property that we had. But does that also work for vectors when you are talking about directions? And the answer turns out to be yes, it does. So for instance, if I would take two vectors, right? So within here, so I have v1 and v2. So let's imagine, okay, that v1, okay, is for example this. So this would be my v1 vector. And then let's imagine that my v2, so maybe my v2 is, okay, this, okay, in terms of its vector. So let's say this is v2. And what I want to be able to see is, what is the resultant vector? So what I want to do is, if I took these, right, and if, so this is because of the brackets, that means I will add the two vectors together. Well, we know how to do that. So I can kind of go back in here, or I can use the parallelogram kind of process to find out. But I know that my resultant vector, so right here, so this would have been my resultant vector. So this is simply v1 plus v2. So let me draw that in here. So there we go. That's v1 plus v2, right? And we have a new direction, okay? And then we also have a new magnitude for my resultant vector. So I'm going to call this the resultant vector r. And now if you took this, right, and you multiplied it by k, okay, so you had my resultant vector, and then you would say this is just k multiplied by the resultant vector, okay, and you would get some result. Now, of course, it depends on the k, right? So the k would just scale it up or down, or possibly if it's negative, it's going to change its direction. Now, this is exactly the same thing. So if you're going to be doing that, it's the same thing if you're going to be distributing the k across. Now, to make this kind of worthwhile for us, let's actually, instead of just having a general k, although it works for general k, let's assume that this was 2, right? That the k was equal to 2. So what would this be? Well, I would have my resultant vector. I'm going to duplicate it. And what I would have is, so this is one of them, okay? And then I duplicate it again because I'm saying it's 2. So this would have been my resultant vector, okay, as a whole, right? So this is what I would have. Let me just kind of match it up in there, okay? So that's my r. So this is now 2 times my r, right? And that's the left-hand side. Now my right-hand side, what I would have is, okay, so this is what I would have. So let me take this out of the way, okay, within here. So I'm going to shift this back out, okay, over here for the moment. And now on the right-hand side, okay, of the equation, so after the distribution, so what would I have there? Well, here are my vectors. Okay, so here it is. I'm going to just steal them. So this is one of them. Okay, I'm going to duplicate it. Okay, I'm going to bring it down actually. And notice that it says is you're multiplying by k. So this is twice as big. So I'm going to duplicate this. So I am making that, so 2 times v1. So this is going to be 2 times v1. That's my resultant vector there. Plus, right, this right here, which is going to be 2 times v2. So I'm going to duplicate this for myself over here. Okay, and so now it's 2 times that. So here's my other resultant vector. So now notice, so if I'm going to be adding them together, so here visually, what would happen is, so I'm going to add them together, and then so here's my resultant vector right there. So I have to go all the way Let me just put the arrow there as well. So there it is. Okay, and that's my resultant vector, okay, within here. And this, this was 2 times v2. And now these two were supposed to be equal. Well, I can take the one that I had over here, right? And I'm going to steal it. Oh, that's not what I wanted. I didn't want to change it in any way. Okay, so let me try to see if I can steal it back. Okay, and notice that if I drop it right on top, they're exactly the same. And that's pretty neat, right, to be able to see that. And that's what the left-hand side and the right-hand side mean. That's the distributive property. So you can distribute a scalar into, okay, the addition of two vectors. That's what the distributive property is all about. So that's this one. And it's not shocking, okay, because you are so used to doing this. Of course, you haven't done it with vectors because you have directions, but it does apply to vectors as well. Now, the associative property, okay, as you're going through this one, so I've kind of written it out, okay, in 2 stages in here. So let me copy this, maybe bring it down right here to try to explain it. So what does this mean? Well, the associative property, again, shouldn't be shocking. So if you do have 2 scalars, right, in front, so notice you have k1, k2. So if you had something like this, k1 times k2, and this is, okay, multiplying through a vector. What you can do is you can first do the multiplication of the 2 scalars. Let's say the scalars were maybe, let's give it some kind of a number. So let's say this was 2, and let's say this was maybe 3. All right, so this is what I have. And, my actual vector, okay, so what I would have, let's say my vector in here, let's say this was my vector v. All right, so this is what I have. So now if I multiply these two together, right, so k1 times k2, I'm going to get 6. So 6 times v, well, what this would mean is I would have to multiply this 6 times. So I would have to duplicate it 6 times. So here is 1, here is 2, okay, here is 3. I'm going to be running out of space here. Here is 4, okay, and indeed I'm going to run out of space. Here is 5, all right, and I guess here's 6. I'm going to try to squeeze it out. Okay, I got lucky. So as you can see here, so this is maybe too many. 1, 2, 3, 4, 5, 6. That's right, it is too many by 1. So let me delete this. So that's what you would have in here, and that's exactly what the meaning is, that you can take this, multiply the 2 scalars, and then distribute it across, and basically says you have 6 of your v vectors. And this is my resultant now. So my resultant would have been this entire, okay, right here. So that is my R. And that R is equal to 6V. Now, what the associative properties tells us is that we can instead actually do the multiplication, okay, of one of the numbers, right? So you can take K2, or as you can see there at the bottom, you could have distributed K1, because multiplication of 2 scalar is commutative, right? So 2 times 3 is the same as 3 times 2. So the order doesn't matter. So I'm just going to concentrate maybe on this one right here. So let's assume, okay, that this, what I have, so this one, okay, let me duplicate it, bring it down right here. What it tells us is it says you can just take, now my K2 was 3, so you can say this is 3 times V, right there. Well, 3 times v, so that would have been 3 of these. Okay, so let me duplicate it, bring it down. So that is 3 of those. So I can do that first, right? So I can say 3 v's, and then I can say I can now take that result. So I'm going to take this entire result right here, and now I can multiply it by k1, and it says 2 of these. Well, 2 of these, so if I do this and I duplicate it, well, now I have 2 of them, and if I put them back to back, of course, as you can see there, I'm going to get 6v. That's what the associative property says. That with scalars, you can multiply the two scalars together and then scale the vector, or you can multiply one of the scalars times the vector, and then the result can be scaled by the other vector, and you're going to get exactly the same thing. So that's the associative property. Now, the next one, the identity property, so there's actually not much to say here. So the identity property is, and what it tells us, it states that if you're going to be multiplying by 1, so if the scalar is actually equal to 1, it doesn't change the actual vector. So what it does is it gives us the vector back. And that's why it's called the identity property. So it just gives us the vector back if you're going to scale by 1. Now, I've talked about this in the beginning of the video, right here. I said that, well, what happens if you're going to be multiplying by -1? So this isn't the identity property, but I wanted to put that in here, is that multiplication by -1, what it does is, if you were thinking about this, okay, so this right here, the negative gets distributed in, so it would have been this, it would have been 1, the negative gets distributed in here, so that it becomes the opposite vector, and then, of course, you can use the identity right here, property, which is going to tell us that 1 times the opposite just gives us the opposite back. So multiplying by -1, what it does is it doesn't change your vector's magnitude, it changes your vector's actual orientation. So it flips it back and it's 180 degrees. So instead of going in one direction, it's going to flip, okay, over into its opposite vector. That's all. And finally, okay, so within here, there's a couple of items. Linear combinations. So now that you're going to be multiplying vectors by scalars, so you're going to be scaling those vectors up and down, and you're going to be doing that, right, in various applications. What you do is, if you have multiple vectors, okay, so for instance right here, as you can see, so what I put here, I have one vector v1, another vector v2, and so on. It goes all the way up to vector vn. So it doesn't matter how many you have, 2 or more. If you're going to be adding any of those, and they are scaled, so notice we have a scaling right here, so K1, K2, these are just scaled and so on. We call this a linear combination. So combination makes sense. You're combining vectors, and linear is because of the fact that you are combining vectors that are only scaled by a scalar. Okay, so that combination, okay, is actually called a linear combination. And in fact, okay, what you can do is, although we typically with vectors, because if it was a subtraction, we know that's an addition of an opposite, but you can also put the negatives in here, right? So it's either addition or subtraction, and it's still a linear combination of vectors. If you go on into learning a little bit more about vectors, typically in linear algebra, for instance, you're going to run into this linear combination quite a bit. And it's just simply an addition and subtraction, okay, of vectors that are scaled by some k. And then finally, another definition for you, collinear. So if you hear this word, actually collinear, I believe it's with 2 L's. You can double check that, but I do believe that it might be collinear. Okay, so it might be 2 L's. Could be wrong. Okay, so luckily I am, teaching sciences and math, although I should know my spelling, so I apologize. But the word collinear, what it means is that you're going to have, if you have 2 vectors, and you take them tail to tail. So tail to tail means, well, this is the tail, right? And this is the head of the vector. So tail, okay? And this is the head. So if you take them tail to tail, right? So if you drop them on top of each other, they will be, they're parallel to each other, so the direction's the same. But if you take them on top of each other, as so, notice the red one actually disappears behind it, that is called collinear, that they're in the same direction and they're on top of each other. They don't have to be the same magnitude, but they are actually on top of each other. So you have two vectors that are collinear. It's different than saying that they're just parallel, because parallel, right? So you would this, okay, if you have a vector which is right here, these two are parallel vectors, right? This one on top of this one, they're still parallel, but they're also collinear, that they're in the same line, the same direction. Magnitude can be different, but they're in exactly the same direction. This, if they're like that, they're just simply two parallel vectors, but they're not collinear because they're not on top of each other. All right, so that gives you a sense of these scalar multiplications. I don't think that it's anything shocking to you. You know, you're going to be running into some examples, I'm sure, in your studies, but I hope that this gives you some kind of an explanation of the properties. It gives you some intuition where those properties come from when I was drawing things out. And it really just tells you multiplication by scalars will scale our vector up or down, doesn't matter. It doesn't change the direction if the scalar is positive. And if the scalar is negative, then it does change the direction so that the vector becomes its opposite, and then that opposite vector gets scaled, okay, depending on the actual magnitude of that scalar. All right, thanks for watching, and we'll see you in a future video. Okay, cheers everybody. Bye.